In this video, we will study the motion of a pendulum under gravity. This is another application of integration to mechanics. This slide has everything, so if you're taking note, everything you need is in front of you. There is this first part where we explain what the situation is, and then this is the summary of all the results we will get. We will just prove those results in the slides to come. That's a summary of what we get in the end. So let's see what the situation is. We have an object with mass m, which is hanging from a fixed point here and attached to a rope. And of course, when you do this, you've seen then the thing starts oscillating, right? So what we assume is that initially you pull your object to the side, stop it until you get to an angle of theta 0, so that's your initial position. At that point you open your fingers and the object starts going. In terms of notation, we decided to denote L the length of the cord. We denote theta, the angle from the vertical, using the usual convention we have in the unit circle. We count positively the angles going this way. Of course, in this notation, m is the mass of the object, g is the acceleration of gravity, and t is the tension of the cord. The first thing we want to do is to establish the equation of motion, which describes how the object is moving. And we are told that once we do that, we're going to get to this differential equation where the variable is theta, and we can establish that the second derivative of theta will be equal to minus g on L times sine theta. Let's do that. Can you already guess where this second derivative is going to come from? Probably, because it always comes from the same law in dynamics, namely Newton's second law of motion. This is the law that says that the sum of the forces applied to an object is equal to mass times acceleration. So the plan is to describe the forces, so there will be two of them. The force due to gravity, here, and this is what brings the object to the center. See, if the object is on the right here, your force of gravity can be decomposed as the sum of these two vectors. So this one plus that one. This one compensates the tension, so your object stays on the circle. And this one brings it back to position of equilibrium here. Now, if your object is on the other side, again, gravity will be vertical, and really it will be the sum of two forces, one in the direction of the tension, so this and that will compensate, so it can stay on the circle. And also one component will be this force, which brings it, again, to the position of equilibrium. And then the tension of the rope. I mean, if there was no tension, the object would just fall on the ground, so that's what prevents it from falling. We will then write, using Newton's second law of motion, that the sum of the forces is equal to mass times acceleration. And the second derivative will come from the acceleration, so we should be able to get this formula. Let's try. We will be writing the coordinates of all of these vectors using the basis vectors I and j. Vectors are not attached to any place, so if you'd like, you can redraw I and j here, and I and j are unit vectors, so maybe I should write them with little hats. Let's start with the easy force, and that's going to be the force of gravity. So the force of gravity has no horizontal component, so we get 0 on vector I, and then if you look at that, it's opposite to vector j, so what we get is minus mg for the vertical component. Okay, that was easy. Now we want to find the coordinate of the tension of the cord. So the tension of the cord is represented here. It's this. Maybe we can zoom on this in order to see a little better. First, maybe you remember from your 7 this configuration with this Z shape and parallel lines. These are alternate angle on parallel line. It means that this angle is also equal to theta. That's this angle here. So we want to find the coordinates of vector t. Cosine is adjacent over hypotenuse, so we can see that this distance here will be t times cosine theta. But this is just a distance, and we need to adjust the signs. The tension of the chord is always pointing up, so its vertical component is always positive. And with theta between negative pi on 2 and pi on 2, t times cosine theta is also always positive, so they're equal. This distance there, it's opposite of our hypotenuse. The length of the hypotenuse is t, so we say they're going to be a t sine theta. If theta is between 0 and pi on 2, your pendulum will be on the right of this equilibrium position, and the tension on the chord will be like that, so its horizontal coordinate here, tx, will be negative. At the same time, since sine is between 0 and pi on 2, sine will be positive. That means that t sine theta is positive and you want something negative, so you need to add a negative sign at the front. Now let's just double check that this also works when the pendulum is on the left of the position of equilibrium. So that's the vertical direction, your pendulum is on the left, that's your theta. And since we're using the usual orientation for the unit circle, this is why your theta is negative. The tension of the chord is like that, and this time its horizontal coordinate is positive. Since the angle is between minus pi on 2 and 0, the sign is negative. So now, sign is negative. There's this minus sign at the front, so minus times a minus is a plus. So by putting a negative sign at the front, we get something positive. So we see that adding this minus sign at the front works in all cases. If you're thinking, there has to be a better way, well, there is one. And as usual in trigonometry, this better way is called the unit circle. I see exactly a unit circle. This angle is theta plus pi on 2, so I know that the coordinates are cosine theta plus pi on 2 and sine theta plus pi on 2. And if you know your trig formula, you know that adding pi on 2 is the same as taking the derivative. So you're going to get your minus sine theta and cosine theta. Anyway, you get the same results. Now we have our two forces. So we have done this side of the equation. So we need to find the coordinates of the acceleration vector. Let's do this. We're going to get the coordinates of the acceleration vector by differentiating the position vector twice. So the first thing we need to have are the coordinates of the position vector. And again, let's just redraw the part we need. So I'm just redrawing this, and the position of my point is given by r. This angle is theta, and I'm going to do the exact same thing. I can either use the unit circle and say that this angle is 3 pi on 2 plus theta, or I could just use year 9 trigonometry and adjust the signs. From the reaction of the people when I did this in class, I'm just going to stick to that. The position vector has two coordinates. Let's first look at the horizontal one, which can also be seen here. Using this right angle triangle, where the hypotenuse has length L, because that's the length of the chord, we can see that this distance right there is going to be sine times L. Okay, now we need to adjust the signs, and we can see that when theta is positive, then this distance would be positive, so we can keep it as that without putting a minus sign in front of it. Let's now look at this vertical distance. We can see that if we do adjacent over hypotenuse, we get cosine theta. Therefore, this distance is equal to L times cosine theta. Now it turns out that when theta is between negative pi on 2 and pi on 2, cosine is going to be positive, but our component needs to be negative, hence a negative sign there. So we find the coordinates of the position vector by finding the distances on both axes, here and there, and then by deciding whether we needed to keep it as that or put a minus sign in front of it, which I call adjusting the sign. I guess I can't resist doing it with the unit circle. How to get the coordinates of the position vector using the unit circle. So since this distance is L, your position vector will be equal to L times a unit vector. Your position will be equal to L times a unit vector. The coordinate of this unit vector are cosine and sine of the angle between the positive x-axis and your vector when you rotate in the positive direction. And this angle is going to be pi plus pi on 2 plus theta. Well, we know exactly what happens to sine and cosine when we add pi to the angle. If you have some angle there and you add pi, you get this point on the circle, and that changes the sign of the cosine, as you can see on the x-axis, and it also changes the sign of the sine. So we can confidently write that this is equal to minus cosine of theta plus pi on 2 and minus sine of theta plus pi on 2. Okay, so we get rid of the problem of having a pi here. Now we have this plus pi on 2, which we had in the previous time. So we're going to be using the same trig formula that says that adding pi on 2 is the same as taking the derivative. The derivative of cosine is minus sine, so with a minus times minus we get a plus, so we get sine theta. And the derivative of sine is cosine, so we get minus cosine theta. The unit circle is your best friend when there is some trigonometry around. So what we have now is position, and remember that our goal was to be using Newton's second law of motion, so what we need is acceleration. We will get it by differentiating position twice. Remember that when we want to get velocity, we're differentiating with respect to time, not with respect to theta, so we'll need to use the chain rule. So that's a constant, we can keep that. The derivative of sine is cosine, but then I need to multiply by the derivative of the inside function. And the derivative of cosine is negative sine, so I'm going to get sine theta times the derivative of the inside function. Theta dot is common to both coordinates, so I can pull it at the front and rewrite my vector this way. Now, in order to get the acceleration, I'm going to differentiate the velocity with respect to time. So L is a constant, so I don't need to worry about it. But here, this depends on time, and that depends on time. So I will be using the product rule. So that's going to be my U, and that's going to be my V. So U dash is L theta double dot, so U dash V plus U V dash. So again, I differentiate these components one by one, keeping in mind that I'm differentiated with respect to time, so I need to use the chain rule. The derivative of cosine is negative sine, and I'm going to use my chain rule. The derivative of sine is cosine. And again, because of this common factor here, I will pull it outside. What I get in the end is this formula for acceleration. We are now ready to use Newton's law of motion. Let me remind you what the forces were. The force of gravity at components equal to 0 and minus mg, and the tension on the chord at coordinate t times minus sine theta and cosine theta. Let's write Newton's second law of motion. So the sum of the forces, so that would be gravity plus the tension of the chord, is equal to mass times acceleration, and I'm going to get mass times acceleration by just multiplying this by mass. And this is what we get. Now, if we use the first coordinate, that gives us one equation, and if we use the second coordinate, that gives us a second equation. Let's write those down. See, I'm rewriting only the first coordinate each time. I put the negative signs at the front because it's slightly more readable. And now, when a number multiplies a vector, this number really multiplies each coordinate. So my second coordinate will be t times cosine theta. And same thing for the next one, the number ml theta double dot multiplies the second coordinate of sine theta plus ml theta dot squared cosine theta. Our goal is to get a differential equation involving g and l, so we don't want t. As a result, we would like to eliminate t from these two equations. And that's something you'll learn to do when you were solving equation by elimination. For example, if you have this system of equation, I'm choosing the numbers randomly, so probably it won't work out too nicely. And let's say you want to eliminate x. What you could do is multiply the first equation by 3, which means multiply each term by 3, and that's going to create a 6x. If you multiply the second equation by -2, that's going to create a -6x, and as a result, when you add them, the x's will be gone. So if I call this first equation I and the second equation II, then when I do 3 times the first one plus 2 times the second one, what I will get is 3 times 2, 6x's, minus 6x's, 0x's. And now for the y, I get 3 times 3, 9x's, minus 8x's, so that's just y. Now the right-hand side. So we get 3 times 5, that's 15. And then -2 times -9, and that's plus 18. And that's 33. So that's the method we were using when we were doing elimination if we wanted to get rid of one of the variables. Here we're going to do this in order to get rid of t. So we want to multiply the first equation by something, the second equation by something, and then add them such that the t's disappear. So let's choose our coefficients. Here we have a minus sign, and here we have a plus cosine. So what would work is to multiply the first one by cosine theta and the second one by sine theta. Indeed, if we do this, we're going to be getting minus t sine theta cosine theta, and here plus t cosine theta sine theta. So that's going to be a 0 here, and that's exactly what we want. So let's see what we get when we multiply the first equation by this coefficient, the second by this one, and then add. So this coefficient is going to be multiplying each and every term, including the first one. So we're going to get minus mg times sine theta. We already said that we were getting zeros for the t's. Now let's look at this one. We have a common factor, which is ml theta double dot. And then we get cosine squared plus sine squared. Hey, that's 1. So I can just write times 1, or even write nothing. Let's look at our next term. We have a common factor equal to ml theta dot squared. And then what do we get? Minus sine theta cosine theta plus sine theta cosine theta. So it just cancels. Times 0. So in the end, what we get is minus mg sine theta is equal to ml theta double dot. So close. We see that there is an m on both sides, so we can just divide by m. And we get minus g sine theta is equal to l theta double dot. Okay, now we can divide by L if our goal is to get theta double dot, which is the second derivative of theta with respect to time. And if we divide by L, we indeed get minus GL times sine theta, which is the result we wanted. This trick of multiplying each equation by something and then adding to eliminate one of the terms, one of the variables, is really a great one. You should keep it in mind. So here are the results that we were trying to establish. So the equation of motion governing this situation is given by this differential equation. That's what we just did. So y is theta of 0 equal to theta 0. Well, that comes just from the story. That's the vertical line. We assume that initially the pendulum was pulled with an angle of theta 0, and at t is equal to 0, the person would open their finger and the pendulum would start oscillating. So initially, the initial angle when time is 0 is theta 0, and this is what this says. This second condition, which says the derivative at theta when time is 0, comes from the fact that the initial velocity is 0, because we decided that when time is 0, the person just opens their finger, they don't push the pendulum. So the initial velocity is 0, and this is what this says. We now have established this differential equation and these two initial conditions. So the good news is that we have established this differential equation which describes motion. The bad news is that we don't really know how to solve it. We would need to use a function called elliptic functions, which we don't know yet. But there is something we can do. When theta is small, theta in radian, remember that the limit of sine theta over theta as theta approaches 0 is 1. And you could see this by looking at the unit circle. So this is a unit circle, and say we choose a relatively small value of theta. Theta really is this distance, using the formula that the length of a portion of a circle is radius times the angle in radians, and in this case the radius is 1. Now sine theta is the vertical coordinate of this point, so sine theta is the length of this green line, whereas theta is the length of this curve. And you can see that if theta is small, they will be very close to each other. And this is where the limits come from. In other words, if theta is small, sine theta and theta are close. So what we do is take sine theta and sub in this formula, and we get this new differential equation which is valid for small angles. As you can guess, if you start from a small theta 0, that's the initial angle, then your pendulum will swing this way and theta will remain small. So starting with a small angle guarantees that theta will be small. If theta is small, you can do this substitution. For small angles, our differential equations become this, and we still have our initial conditions. And now we recognize something. The second derivative of something is equal to a negative constant times something. We've seen differential equations like that, and we know exactly what the solution is. We know that in order to solve them, we just need to rewrite the negative constant as minus the square of something, which we can do if we decide to let omega be square root of g on L, and it looks like this. And in that case, we've seen in a previous video that the solutions of this differential equation will always be of that form: a constant times cosine omega t plus another constant times sine omega t. And then, depending on your initial condition, you can find the values of a and b. So we have proved that theta has to be of the form a constant times cosine omega t plus a constant times sine omega t. And now we use the initial condition to determine what the constants are. We know that when t is equal to 0, theta is equal to theta 0. So we sub in t equal to 0, and we get a cosine 0 plus b times sine 0. And if you look on a unit circle, 0 is there, cosine is the horizontal component, sine is the vertical one. So since the coordinate of this point has 1, 0, cosine 0 is 1, and sine 0 is 0, so that's a. So we already found what a is. A is theta 0, the initial angle. The other initial condition we have is that the initial velocity is 0. That is the derivative of theta when time is 0 is 0. So we would like to sub in into the derivative of theta, but we don't have it yet. So now the plan is clear. We first calculate the derivative of theta with respect to time, and we just use this. So we know that a is theta 0, that's a constant. The derivative of cosine is negative sine. And because of the chain rule, we need to multiply by omega. So same thing with the second term. B is a constant. The derivative of sine is cosine. And we multiply by the derivative of the inside function. So when time is equal to 0, then this derivative will be 0. And that means that 0 is equal, well, we've done that earlier. Sine 0 is 0. Cosine 0 is 1. So we're going to be getting 0 plus b omega. So b omega is 0, and if we divide both sides by omega, we get that b is 0. As a result, we now know that this a is theta 0, and this b is 0, which gives us this formula here. And in all these calculations, omega stands for the square root of g on L. Having this, it's easy to find the period. So some people just know a formula for the period, which is t is equal to 2 pi on omega. I'd like to establish that. Let's say capital T is the period. So when you add the period, you get theta 0 cosine of omega of t plus the period, which is theta 0 cosine of omega t plus omega times the period. And you know that when you add the period, nothing happens. You're back to where you were. So cosine omega t. So that means that the fact that you added this omega t inside cosine made no difference, right? Because that's the same, and you have this cosine, so these two cosine need to be equal. The smallest value of capital T, the period, which will make this happen, is if this is actually 2 pi. And this is where your formula comes from. If omega times the period is equal to 2 pi, then the period will be 2 pi divided by omega. And 2 pi divided by omega is exactly this number here. We will now use the results that we have established. Question 1. If a pendulum is 9 meters long, what is the period of the pendulum? Because indeed maybe you've noticed that if you take a really long rope, then the oscillation will be long and slow. If you take a smaller one, it would be much faster. So indeed, knowing the length of the rope should be enough to tell what the period is. So let's use the formula that we just proved. The period is 2 pi times the square root of L on G. So here we want the period, so we can use this formula directly. 2 pi square root of L on G. L is 9 meters. G is 9.81. If we put this in the calculator, we get something really close to 6 seconds. Interestingly enough, the period doesn't depend on the mass, just on how long the cord is. And of gravity on Earth, but okay, fine. Question 2. To make a pendulum with a period of 1 second, how long should the pendulum be? Same idea here. The period of the pendulum depends only on how long the rope is. So if we calculate smartly the length of the rope, we can decide what the period will be. And in that case, we want a period of 1 second. So 1 second, the period should be equal to 2 pi square root of L on G. And now it's just an equation where we're trying to find L. So we could divide both sides by 2 pi. Then we could square. And now what we get is L on G, and we just want L, so we can just multiply both sides by G. And we get L is equal to G on 4 pi squared. We sub in, and we get 0.25, because everything was expressed in meters, and we can see that that's 25 centimeters. Conclusion on simple gravity pendulum. The trick we used to solve our differential equation, which was to say that sine theta and theta were approximately equal, and we said that worked because theta was small. In fact, it works fairly well even for reasonably large theta. So the solution we have is theta is equal to theta 0 cosine of omega t, and that describes a pendulum that would swing forever, right? What we would have is, so this angle would be theta 0, that would be our initial position, and then the pendulum would go from one side to the other forever. You can also see this if you represent theta against t. What this tells you is that, so let's say initially your angle is theta 0, you're here, then the angle decreases until it becomes equal to 0, so you're getting there, then the angle becomes negative, and if we decided to count the angle the way we do on a unit circle, we totally believe that once we go this way they become negative, and then it would get to negative theta 0, which is exactly what would happen when we get there. At this point there is a horizontal tangent, which means that the derivative is 0, so it stops, and then theta starts increasing again until it goes back to 0. So that's when your pendulum goes the other way and start going back. So what both of these things show is that your pendulum will swing forever. Now in real life you've seen that it doesn't swing forever, it ends up stopping. And this is for two reasons. First, there could be some friction at this place at the top where your pendulum is attached, and also because there will be some air resistance acting on your object and pulling it back. But it's interesting to notice that in practice, what will make the pendulum stop is not gravity, it's actually air resistance and friction at the top. So thank you for watching this hard video, I have to say, on simple gravity pendulum.